Guys, we're all ready to go with the next one, part 4 on our spotter training. So let's dive right in. We're going to be talking about multicells. Now, we've already had a good discussion on multicell storms, and we said that the dominant feature is what's going on along the gust front. And we said that we have to lift air along the gust front, not just to the LCL, where we could get a shelf cloud, but we need to lift it to the LFC, the level of free convection, where we're able to generate new convection. So when I look at this diagram, this picture, I'm looking at basically 1, 2, 3, 4, and then kind of a growing 5th thunderstorm here. We're looking at multicells. So the fact that this one over here, and there might even be another one over there, but that these storms are kind of flattening out, the anvil is all kind of smooth and glaciated. This is probably the dissipating stage. This is the tallest one. These ones are growing. These two might be mature. And so we want to think about the tops kind of defining what it is. Remember that every storm is an updraft or is an updraft, downdraft couplet. Okay, we said multicell storms can either be clusters or squall lines, and that's just something that you really need to know. Okay. Now, how many cells do you have here? Now we're looking at about the same thing that we saw in the last picture. I've got the anvil of 1, the anvil of 2. Here's the big guy in the middle, and then maybe 3, and then this one over here, 3, 4, 5. Now, what I see is different is that this is definitely tallest. This is all rock hard. Do you see the texture being all cauliflower-like here? So rock hard texture is probably growing. But if you look closely, do you see anything over here? Now, you can't really see any sort of like details. This is because there's rain falling in there, and rain obscures your vision. But if you look closely, and I hope you look closely, is we can actually see the rain-free base over on this guy. So that this guy has a rain-free base says that the rain is not falling. It may be developing, and if it starts to fall, it's probably going to fall out down sheer, somewhere like this. So this is maybe in the developing stage. These two might be mature. These two are dissipating. Okay, so we kind of get those clues to what's going on in the storm. Okay, so what did we just see on there? Now we're going to look at an RHI. And we're going to say that here's the big guy in the middle, the heaviest precipitation, and it is starting to generate an outflow boundary. So the cold pool spreading out. Here's the RHI reflectivity that's put on the picture itself. What we're saying is that up in the cloud is where precip starts to develop. And I said that you start to see those echoes around -15 C. That's where you're going to start to really see reflectivity. So you got to get the updraft going up to at least a temperature of -15 degrees C. So you can see that even though we're starting to develop precip aloft, it's not making its way down. 3 is definitely in the mature stage, and the heaviest rains, especially in this one, are down near the ground. This is the cross section from A to B, which says on a PPI, this is what we're going to look at over here. So where's the greatest threat of severe weather? Well, the greatest threat of severe weather is in that region, which would correlate to somewhere in this area. And when I say severe weather, I'm talking about large hail or damaging winds. Okay, probably not getting a tornado, but obviously a tornado could possibly form, especially if it's almost more of a land spout tornado. We're not assuming that this is going to be a strong amount of shear causing mesocyclones and therefore supercells. This is just enough to get airlifted to the new LFC. What we find out is that as this cold air pushes out, that's going to lift other air up and over it. So you're going to increase that gust front, and you're going to create the lifting going on there. And so this cold pool, as you would get in this area, cold pool, is going to undercut cell 4. So cell 5 will start to dominate, cell 4 will become mature, and then start to die out. So cell 4's rains are going to kill cell 3. Cell 3 kills cell 2. So what we're saying is that the child cell kills its parent. It's almost what we call patricidal, killing your parents. Okay? We know that new updraft growth is going to be preferentially on low-level convergence. So I want you to know this statement here, and I'm going to type it out to you. Two things about multicells you need to know. Each cell moves with the mean wind of the cloud-bearing layer. Guess I can move that here. The second thing is new cells grow where the low level convergence is strongest. So in other words, on this diagram here, if I'm looking at the air coming out this way in the cold air and the warm air is coming in this way, then this area is where new cell growth is trying to go. That's where it's going on. And that's cell 4. So this whole area is very convergent, and the strongest area is going to be where that is. Now we have to take in mind the low level shear. We talked about the shear has to be opposite in direction of the shear generated by the outflow boundary along the gust front with the buoyancy gradient. So go back and review that, put that in here, and then you get those oppositely but equal magnitude vortex circles lifting the air. Now, what does that look like overall? Well, I'm going to do this. I'm going to go ahead and erase all this stuff here because I don't need that. I'll keep this information. So imagine this, guys. Imagine that I've got a cell that forms someplace. And we'll say that this direction is the mean wind. So this cell is going to go with the mean wind. So we kind of imagine the cell growing, getting to its mature stage, and then as it goes further, it starts to dissipate again before it dies. So that's the evolution of this cell. We'll call it red cell. Now, do you agree that red cell is going to create an outflow boundary? And even though it's not exactly symmetric, for the sake of learning, I'm going to pretend that it is. So imagine that this is looking down at the cold pool. I'm going to write the little gust front, which is a cold front. So that's the outflow. And you have to think of that the air is diverging underneath this thunderstorm, right? And then we go back to our kinematic flow field. Fair enough? I don't know why I have that extra arrow. I don't think I need all of them. But that's what it is. Fair enough? Say yes, Paul. Okay, great. Now, what if the surface wind were this direction? So we have the mean wind out of the southwest, but the surface wind is out of the east. So we'll call this surface. In other words, there is flow going into this storm that is all pointing in the same direction. So I want to imagine, I want to get an arrow. Imagine that all the air is flowing this way all around the storm. Fair enough? Where will the low-level convergence be strongest? Well, the low-level convergence should be strongest on the southern flank of this outflow. Because is this convergent going this way and going this way? Sure, like T-boned by a car. Is this convergence? Well, it depends on how fast it is, because you're all going in the same direction. You could be going faster than the winds and you're bumping into you could go faster than the car in front of you and you'll bump in from behind them. But where will the worst accident be? The worst accident is here to the south, where you've got the air moving directly at each other. So what that tells me is I'm going to get a new cell forming where the low-level convergence is strongest, which is there. But which way is this storm going to move? Well, it moves with the mean wind of the cloud-bearing layer. So it grows up, matures, dissipates. Where will the new storm be? Let's call it orange. The new storm will form to the south of the mature cell. It will grow, it will become large, and then it will die out. Okay? And if I did one more storm, oh, I don't know, let's go purple. There's purple, grows up, and it dies out. Now, if you're standing here and you're looking this way, what you've seen is a big red storm and a big yellow storm and a big orange storm and a big purple storm. You don't know that they're different. It's like the big storm is coming right at you, right? It feels like the storm is moving towards you. Reality is each storm is going off and a new one's developing to take its place. So at any given moment in time, what exists? Let's go ahead and try this. At any given moment in time, what exists is a line of storms north and south. Something along this line. And that's going to continue moving on because this would be like a new storm that develops over here. And so what we have is the line of storms at t equals 0 seconds, let's say. T equals something else, 1. We don't have to say seconds. Let's just say initial time, and then some later time, and then some later time 2, and then t equals 3. It appears as though the line is moving to the east, even though what direction is each cell moving? Each cell is moving to the northeast with the mean wind of the cloud-bearing layer, right? That's the mean wind. So what we have created is that the storm as a line is moving differently than the actual cells. So we say that the line experiences differential motion. Or it, maybe a better word would be deviant motion. And to clarify that, what we'd say is the line movement deviates from the mean wind. And that's the first time we see lines moving in one direction and storms moving in another direction. Okay? Now, let's talk about what would happen if we changed all of this. So I'm going to just erase everything. It's just easier to redo it. This time I'm going to say, what am I going to say? I'm not going to use the same colors because I don't care. I'll say that the mean wind is this way, same way, but the surface wind, the winds coming at the ground at low levels, is this direction, same direction. So it's storms are moving from the southeast or southwest to northeast. The winds are from the southwest. So what's going to happen? Well, I'm going to start with the storm that grows, becomes larger, and dies. This puts out an outflow boundary going all directions equally, right? Diverging. Even though that's not necessarily true, let's just pretend that is the case, right? We know what divergence looks like. Based on the surface wind here, surface wind, where will the convergence be strongest? With this arrow in green pointing this way, it's going to be down there. So where will the new cell form? Well, the new cell forms here and it moves this way. And where will the new cell form next? It'll form here and move this way and move this way. So at any given moment, which way is the line of storms? Well, the line of storms is like this. And which way is that line moving? Slowly moving this way. But if you were standing, imagine this, guys. Imagine you're standing here. The blue storm is raining on you. A little bit later, the yellow storm rains on you. A little bit later, the purple storm rains on you. Pretty soon, you're just experiencing rain after rain after rain, and you start to get flash floods. Each storm is moving over the track of its parent. We say that these echoes are training, or they're train echoes, because they're traveling over the same track. And that leads to flash flooding. Winds are all going the same direction. Storms are very moving, not very fast. In fact, back in the 1995, about like that, there was a series of multicell storms that formed over Naperville. And Naperville overnight was under this train echo. It just kept forming along the front, and storms formed from around 5 o'clock till 6 in the morning. So maybe 12, 13, 14 hours of rain. They had 19 inches of rain overnight. Amazing amount of flooding. If any of you have parents from Naperville area, they will remember that if they were around in the mid 90s. So that would be what's happening here is you get train echo. So depending on how the mean wind and the surface wind are blowing, you're going to get some different structures of how storms behave. Okay, now keep in mind that all of these things, let me get rid of this, all of these things are multicell clusters, right? We're looking at a cluster. New cells form at a preferred flank, which is what it says in bullet point number 1. And that preferred flank is where the low-level convergence is strongest. Okay? Here's the time evolution of a storm. By the way, we're out here. This is as far north just about as we've ever been. We were in Prince Albert, Canada, watching a storm off to our northeast in the middle of July. So we've got these big thunderstorms going. The anvil is really nicely formed all around it. Each cell is moving away from us, and new cells keep forming behind it. And so we see this really great evolution of a multi-cell storm. So here's what's going on. Cell 3 starts to rain. Cell 2 is the dominant storm. But as 3 starts to rain, the gust front surges out, keeps lifting the air for a while, kills off storm 2, 3 becomes dominant. But as the gust front continues to go out, it starts to lift air, cell 4, who will eventually become the dominant storm. Okay, so we're looking at a series of evolving storms forming into some sort of a line segment. That's called a multicell cluster. Here's an example of some clusters. We are looking here at an isolated storm right over there. So there's the anvil of this isolated storm. If a storm is isolated ahead of a line, that's usually a bad sign. That's usually a significant storm. But over here, I've got top, 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 top. So I have basically a little cluster of storms moving this way. Little bit of a gap there, and then I've got top, 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 and here's some new ones developing. So I've got like a new multi-cell cluster forming. So I've got 2 clusters. This is what we might call back building. It's really just building to the southwest because the winds are probably somewhat southerly at the surface, and that's where the convergence is going to be maximized. Excuse me. Now I've seen this. We're out chasing. This is another time we were up in Canada. We're actually looking to the south. So we have updrafts that are forming. Here's sort of the flanking lines, and you can see a little bit of tilt in them. And the storm's going up here. And this is actually a storm here and a storm here. These are awfully close together. So it's basically pulsing up like a series of bubbles. Eventually what happened is the bubbles became so frequent, and we gave it some time that the environment started to rotate. Once it rotated, it started to become a supercell. So it took a long time as a multicell. It eventually evolved into a supercell, which dominated right before sunset. It produced a tornado. So that's a case where the shear is marginal, good enough for multicells, marginal for supercells, but given enough time, you can kind of develop that mesocyclone. Now, when we get into multicell squall lines, there's a difference. This is not a series of cells that form on one location. This is the entire thing. This is the entire line. So the line goes all the way north and south. And where do new cells form? New cells are forming all ahead of the line. So there might be new cells forming all along the line. It's almost like a snowplow pushing out. And the reason for that is that the leading edge tends to have a well-defined gust front. And that's, so the maximum convergence is ahead of the entire line. That's what makes it a multicell squall line. Continuous, well-developed gust front at its leading edge. It's hard to define discrete cells. This is the way you spell discrete, meaning one, each individual storm. It's because, right, it's like, where's the storm? I don't know, it's hard to see. There's like sort of a line of storms. Well, that's exactly what I mean by a squall line. So rather than being at a preferred flank for new development, it's going to form all along the whole line. Anytime you have a high echo core, high reflectivity, now you're looking at the possibility of large hail. Damaging winds are possible. Most likely the damaging winds are going to come in here right behind the gust front. They can also occur further back, so be careful. But most of the time, the damaging winds are along the gust front at the leading edge. Now, sometimes the line, as we see here, becomes kind of wavy. So here's a line in here, it becomes sort of wavy. And when we have that, we have basically air coming this way, surging the line out. And if I have a line of storms, with winds coming in, it forms a bow-shaped appearance in the echoes. And that's what we call a bow echo. Well, if I have a series of these bows, bow 1, bow 2, bow 3, bow 4, then I get what's known as a line echo wave pattern. So you're going to add these things to your acronym list: LEWP, L-E-W-P, line echo wave pattern. It's just whenever you see a squall line with lots of little squiggles in it, then you know you got something. Now, just so you know, there's another name for this. It's called a QLCS. And a QLCS is a quasi-linear, meaning it's sort of a line, this is a line, but it's wavy, convective system. Now, I started going, well, why are you calling it two things? And I thought, well, maybe I'm missing something. I've called line echo wave patterns. Now they're talking about QLCS. And I talked to the guy, his name is Ron Przybylski. He's like probably a leading expert on bow echoes. And I said, well, isn't a QLCS just a line echo wave pattern? And he looked at me like, no one's ever asked me that before. And he thought about it for a second. He goes, oh, well, yeah. I'm like, trying to teach this to people is tough because scientists are not being consistent. And I found out later that a line echo wave pattern was sort of, that's the old school version of what this is. But there was a scientist who did some papers on tornadoes associated with them, and he called it a QLCS. And all of a sudden, it sort of interchanged. So sometimes scientists aren't precise, especially when they're not teaching people who've never had this before, and so they make stuff up. But you know better. Okay, so I want you to compare this schematic cross-section with the supercell cross-section. And what we're going to find out is that there's some major differences. So I'm going to do this. Actually, let me do this for a second. I'm going to pause the share, and I'm going to, what am I going to do? I want to pause the video. Okay, going to resume recording and resume this. So I think I'm recording. Am I recording? I think I'm recording. I hope I'm recording. Pause recording. Yeah, I must be recording. Okay, so I have the cross section of the squall line, and over here I've got the schematic of the supercell. Okay, so we see in both, let's take a look at what's the same. We have the overshooting top, and then we have the anvil. And maybe under the anvil's mammatus. Okay, so in my squall line, I do have the overshooting top, I have the anvil and mammatus. Now there might be some rain from the anvil and it's evaporating, so we call that virga. And when we go to the supercell schematic, we've got some virga. Okay, so these look kind of the same. But then what? Well, let's take a look here. I'm standing here and this thing is approaching me. I will feel the gust front. And then what will I experience is some of the light rain. And as the storm gets closer to me, it's going to get heavier and heavier rain. And then it's going to start mixing in with hail. Okay, it's getting intense. It's pretty brutal. Keep in mind that the tornado comes next. So when I say the tornado comes next, keep in mind that the tornado is always going to be underneath the updraft. So the tornado, write this down, the tornado is an updraft feature. It's under the updraft. Remember, it's a big sucky thing. It's drawing air in and accelerating it up. But we're going to see when we get to the supercell section, the PowerPoints, we're going to see that there is a gap called the visual vault between the updraft and maybe the heaviest rain that you see. There could be some stuff in here that's got hail, and hail doesn't show up visually very well, bright on radar, but not visually. In any event, all the big hail, damaging winds, tornado is all found near the updraft, downdraft. I'm writing this down, it must be important. Interface. Okay, the updraft, downdraft interface. So updraft here, downdraft over here. And where those two are meeting, this region over here, this is the place where we have to be really concerned, right in there, near the updraft, downdraft interface. The hail, the winds are downdraft features. The tornado is an updraft feature. Okay, that's a supercell. So I'm watching the storm get closer to me. It gets scarier and bigger and bigger and bigger and bigger. Hail starts coming, and then all of a sudden we're underneath the updraft. That's where the precipitation stops. That's why people often say it's calm right before the tornado. Because I think what it is they're getting high winds and large hail falling, and then it stops. Plainfield tornado, there were people who were getting their car in out of their driveway because it was like golf ball hail. So they ran out there, they drove the car in, she had her son and she drove the car into the garage. And as soon as she got the car in, the tornado hit. And she saw her son fly across the room, stomach down. And the tornado passed, she ran over, lifted up his shirt, and he was okay. And the kid goes, "No, Mom, I flew." So he had actually flown across the room. The point of that story is that tornado came after the hail. It was the hail that told these people, "I got to go move my car." Okay, not a good idea. But what happens in the squall line? Well, the squall line, it's different. Where's the updraft? The updraft is on the leading side. The precipitation then falls out like this. So when we look at what we'd experience if you're here, you see the anvil, you might see the overshooting top, mammatus, maybe this virga, and then you start seeing a shelf cloud, which is fine because it's along the gust front. But when the gust front goes through, if there's a tornado, it's going to be right here near the updraft. The cold air will then come down like this. And then you get the heavy rain and maybe the hail that falls in here. So what do you experience? Nothing, gusty winds, boom, tornado. And then you start getting hail and rain. So if you're watching a squall line, or if you're ever in a situation where it's hailing and the hail starts turning just into rain, you're probably in an okay place. But if you go and it's raining and all of a sudden it starts to hail and then it stops, that's bad. That's bad news. Now on here, I'm going to do one more thing really important, and then I'm going to probably stop because I want to do this rest in class discussion so that I can answer any questions. But this is super important. We've got cold air coming out, and it spreads out underneath this. The way this diagram is drawn is that they're implying that the warm air, the moist air is also warm, comes up, goes over the gust front, and then it goes up. In this case, if I said, do we have a parcel of air? Let's draw the color green. If I have this parcel of air, is this parcel of air lifted upward to become the updraft? And the answer is no. Parcels are starting out ahead of the storm. They go up over the gust front, and then they accelerate upward as they hit instability. In this case, we say that this storm is elevated. There's many different ways to define an elevated storm. But for now, what I'm saying is that surface-based parcels will not go straight up into the cloud. Surface-based parcels do not go straight up into the cloud. You should stop and write that down. That the parcels are coming up over the gust front and then going up. Elevated storms will not produce tornadoes. Now, could there be incredibly strong rotation up here? Yes. And so on a radar, they may go, oh, look, there's a TVS. I might even see a hook. But if it's elevated over cold air, this is not going to produce a tornado. So when you were talking the other day about if there's a TVS, should I put out a tornado warning? Not necessarily. If I have good clues that it's elevated. But be careful. It takes a while to figure out what those clues are and how cold this air has to be. Just because it's behind the gust front doesn't mean it still can't go straight up. Not in this picture, but just because air is behind a gust front doesn't mean the air can't go straight up. In other words, the air behind a gust front may be colder, but it still might be buoyant. You should go back to what I just said and write that down. And because you have the ability to do that, I am going to let you do that. And that will become super important as we're going into supercells. Okay, so hold on a second, please. I'm going to stop right here because I think this is a good stopping point. And I want to make sure that we can talk about this in class. And then I'll go on for the second half of these slides, which we'll be able to finish completely up. We'll try to do that in class. But I will, for those of you who may be watching this video elsewhere, this will also be recorded. So you can put together information like this. But this is a good place to start. And I just want to underscore the need to know the difference between how you experience a supercell, which is usually the tornado is on sort of the rear side of the storm, as opposed to a squall line, which is on the forward side, the leading side. We had a big derecho this summer, and we had a number of tornadoes in it. Really what we had was a QLCS with tornadoes. Those were not supercells. They were short spin-ups as the gust front passed. So you had the strong winds, but there was still an updraft over that area that was able to stretch vorticity and create additional rotation that did a little bit additional damage than just the straight line winds. So if you're going to get a QLCS tornado, that tornado is going to be really close to the front of the gust front. If you're back here where it's already getting into a lot of rain, you're not going to get a tornado there. You're going to be sort of right up there at the front of this scenario. Okay, guys, that is the lecture for today. Study it. There's a lot of information in there. I think you should be able to understand it alone, but if you have questions, you're welcome to ask me about them. Study it well and do great. Okay, guys, have a wonderful, yay, spring, whatever.